Hi there. In this video we're going to start to develop some techniques that are going to help us find derivatives a little bit easier than the way we've been doing it. If you recall up to this point, the way we've calculated derivative is we've used this limit process right here with our particular function, and that works well for nice functions. But if the function is the least bit algebraic intensive, then this can prove to be quite cumbersome. So what I want to do is I want to use the limit process on this basic equation x to the n and see if it doesn't maybe give us some expression or some rule that we can maybe use for the future. So before we get started, I need to say that this proof requires a little bit of pre-calculus knowledge. It requires you to know something about binomial expansions. If you don't know about binomial expansions, the previous video gives you kind of a crash course in what to do there. So at this point, I'm going to assume you know how to expand a binomial of an nth degree, and we'll leave it at that. So let's get started. Okay, so our function is x to the n, and I've just written it here two different ways, as I usually do, just to reinforce that there's many different ways to express what you're doing. So function notation, y equals x to the n, same thing. Okay, as far as the derivative is concerned, I can say f prime of x, I could say dy dx, I can say y prime, or this fourth one here. A lot of people confuse this with this notation here, and they're really not the same thing. This is an operator. This is telling you to do something on x to the n. It's telling you to find the derivative of x to the n. This is a derivative. We just don't know what it is yet. But it represents a derivative. This tells you to go find the derivative. Okay, so here we go. Let's evaluate this limit statement here, assuming that f equals x to the n. So what is f of x plus h? Okay, f of x plus h is simply going to be my input raised to the nth power, and my input in this case is just x plus h. Okay, minus f of x, which is just x to the n, and this is all over h. Okay, so here's where the pre-calc knowledge comes in, and I want to expand this binomial right here. I want to expand x plus h raised to the nth power. Well, how do you do that? Well, the first term of that expansion is simply going to be n choose 0 times x to the n times y to the 0. Now I know some texts they won't do this combination here, but they'll just call it x to the n. But I want you to see the whole pattern here, because to me it makes a little bit more sense. Okay, plus what's our next term going to be? Well, the next coefficient is going to be n choose 1. And more on this in a minute. And what happened to the exponents on my x variable as we move from left to right? Well, they went down. So this was n. Now it's going to be n minus 1. Okay, and I just realized I made a mistake. This is not y, it's actually an h here, so sorry about that. Okay, that should be an h. And what did those exponents do? This was h to the 0. This is going to be h to the first. They increase by 1. Okay, so let's go on to the next term. Next term is going to be n choose 2. And x, the exponent on x gets decreased by 1 more. This will be n minus 2. And this will be h squared. Now this is going to continue. This is going to continue indefinitely, really, until we get to the end of the term. Well, we don't know what n is, so we don't know how many terms are in here. But I want you to think about what the last term would be. What would the last coefficient be? And we know that it's going to be n choose n. Well, what's the coefficient right before that? Well, it's going to be n choose n minus 1. Okay, and the easiest way to think about this is through the last term. The last term is easy to think about. That's n choose n. And we know that the very last term, the very last exponent on x will be 0, because remember it started at n and decreased by 1 all the way till 0. And the exponent, I almost wrote an y again. The exponent on h is going to be an n. Okay, so what is going to be the exponent on x right here? Well, it's going to be one more than that guy. That'll be x to the first. And the exponent on h will be n minus 1. There's a plus here. And this right here represents, this whole thing right here represents this thing expanded, in expanded form, I should say. Okay, minus this x at n. And I'm running out of room here a little bit, but I think I can get it. There we go. Okay, now this is all over h. Okay, there you have it. Now, let's just go ahead and simplify this a little bit. And I'm going to do several things at once. The first thing I'm going to notice is that n choose 0 is just 1. And if you don't know what n choose 0 is, again, I talk about it in a previous video. N choose 0 is just 1. So this is really 1 times x to the n times h to the 0. And that's just going to be x to the n. Okay. N choose 1. What is n choose 1? Well, again, if I have, and again, this won't make sense if you didn't see the last video, but if I have n marbles in a bag and I only want to choose one of them, how many different ways can that happen? Well, that's going to happen n number of ways. And then that's going to be multiplied by x times n, x to the n minus 1 times h. Okay, plus. Now I'm not going, well, yeah, I will. I'll go ahead and rewrite this here. I have no idea what n choose 2 is. Okay, n choose 2 is going to be contingent upon what n is. If n is 3, n is going to be a certain value. If n is 4, this combination is going to be a different value, so on and so forth. So I'm just going to leave it as n choose 2. These exponents remain the same. And then this goes on for who knows how long. And then I have n choose n minus 1 times x times h to the n minus 1 plus, now n choose n is just 1, x to the 0 is just 1, so I have just an h to the n and then minus x to the n. Okay, and again, all over h. Okay, well, some of you may have noticed already what thing happens right away, and that is I have an x to the n here, it's positive, I have a negative one here, they're going to go away. So those will go away, and at the exact same time, I'm going to also notice that the rest of these terms that are left over, what do you notice about them? Well, they all have an h. Okay, so every term, this is an h to the first power. This is an h to the second power. Then there's an h to the third power somewhere in here. H to the fourth. Until we get up to all the way to h to the n. Okay, well, if you think about it, this h in the denominator can cancel with every single one of these h's up here, with one of them. It's going to cancel with this h to the first. It's going to cancel with this h squared, leaving us with just an h to the first. Okay, it's going to cancel with this h to the n minus 1, leaving us with, what would it be? What would this be instead of n minus 1? Okay, well, it's going to be an n minus 2. And if this h reduces with an h in here, I won't have h to the n anymore. I will have h to the n minus 1. Okay, and then this guy will be gone. Okay, so let's rewrite what we now have. We no longer have this x to the n because he went away with this guy. So I have n times x to the n minus 1 plus, notice it, remember I don't write the h, it went away, plus n choose 2 times x to the n minus 2 h, remember this is now an h, plus a whole bunch of stuff in here, plus, we'll just write the last term here, h to the n minus 1. I didn't rewrite this term. Okay, there we have it. That is everything. This term, understand, just so we're clear, this term right here is somewhere, it's right before. I just didn't write it. It's somewhere in there with a whole bunch of other terms. Okay, well now, looks like we just have one great big long polynomial. And how do you evaluate limits? Well, the easiest way is direct substitution. So if you notice that if I substitute 0 in for h, the only term that does not have an h is this first term. So if I plug in a 0 into here, a 0 into all these h's in here, and a 0 here, I'm really left over with this expression. Everything else goes away. It's like magic. I think that is cool. So we took this, what seemed to be an infinitely long expansion. It wasn't infinite because we know that n just simply represents some finite number. But we took this really long expansion and we reduced it. We reduced it to this nice little expression. Well, what does that expression mean? Well, that's my derivative. Okay, in other words, the derivative of f is n times x to the n minus 1. Well, how do you use that? Well, let's just say you wanted to find the derivative of x cubed. Okay, if you want to find the derivative of x cubed, the way we used to do it is we would have to apply this definition of a derivative to this function right here. And we'd have to go through this whole limit process just to find the derivative of this thing. Okay, but now we have a nice little formula that says if your function takes on this form, x to the n, then what you can do is move your exponent out front and decrease that exponent by 1. So this represents the derivative of x cubed. Okay, one more example just to make sure you have it. Let's use a different form here, different notation. Y equals x to the 5th. Well, what would dy dx be? Dy dx is going to be, you bring your 5 out front, decrease your exponent by 1, and you're done. That sure beats going through two long limit statements just to get to this nice, neat little result. So that's a proof of the power rule. I hope that made sense. I hope that cleared some things up. I would suspect that some of you already knew this, but hopefully now you know why it works. We'll see you around.